From the COVID-19 pandemic to the climate crisis, in the past few years, science has increasingly been taking a central role in public debates. Even when ignoring the more fringe conspiracy theories, the decreasing public trust and increasing questioning of scientific knowledge production has been voiced by all sides of the various national political spectrums and can hardly be overlooked. There are a lot of explanations for this trend, with scientists themselves, of course, mostly blaming the apparent growing distrust on social media, while sometimes on problems with their own science communication, and always the returning lack of science education under the public. In this video, I argue it's rather a more fundamental problem that is inevitably connected to how science is understood in today's society. To make this case, I will first look at how historians of science have tried to analyze science. I will then look at how historians of science have tried to understand Einstein's introduction of the general theory of relativity. To conclude, I will give 5 perspectives from Einstein's introduction of the general theory of relativity that help us better understand science today. Before I start with examining what history and philosophy of science can offer to give this better understanding of science, I think it is first important to show that the current understanding of science results in real, recurring problems and challenges. Indeed, the responses to science in the COVID-19 crisis was not an extreme once-in-a-lifetime situation, but rather an inevitable outcome of this understanding of science. I would even argue that similarities to the COVID-19 pandemic can be found throughout the past decades. From the reaction to Chernobyl, to the debates about SARS in 2008, to the debates about recombinant DNA technology or biopsychology, as well as my personal research on the rise of neurobiological explanations and treatments for mental illness from the 1990s to today. I think the COVID crisis is, however, a good example, as it's still very strongly in people's memories, and more so, I think it was a similar process in most countries, with scientists on the stage alongside politicians, both at the press conferences but also on the media reporting, for example. On the stage, scientists present themselves consistently as mere spokespersons of the scientific truth. Indeed, it seemed as if they find these neutral objective facts on which politicians and policymakers then have to make political decisions. Scientific knowledge production was what science and technology studies scholars call black boxed. This is also the idea of science that many of the public and science journalists, as well as science communication itself, follows. Scientists might be urged to come out of their ivory tower to share wisdom, or some might call to show what actually happens inside this tower, but the idea that scientific knowledge is exclusively composed of elements already available in their laboratories and universities, and that it happens without outside interference or influences is almost universally spread. Hence, most voices in the public debate focus on what supposedly happens on the moment that science or scientists leave this imaginary ivory tower and then interact with politics when it comes to policy-making decisions. The obvious examples that were retrospectively questioned are how, at various stages in the pandemic, for example, differences in national policies on, for example, shaking or washing hands, mask wearing recommendations, types of masks, different opinions on the indoor spread of COVID or booster vaccine recommendations can be explained. The problem is that this means that even in these debates, both sides present science as a separate, isolated sphere from politics. Of course, it might occasionally interact with politics when, for example, policy is to be made, but otherwise, or at least ideally, should be autonomous. The reason why I and other historians and philosophers of science think this is problematic is something that I hope to cover more extensively in a future video. For now, I think that the negative consequences of this idea, on the one hand, can be understood as that it's continuing a limited, a flawed understanding of scientific practice and thereby of what exactly is scientific knowledge. On the other hand, it is also flawed because the public understanding of scientific knowledge itself is also vulnerable. What this leads to, as I think highlighted very well by 2 prominent historians of science, Naomi Oreskes and Eric Conway, who in their recent book, Merchants of Doubt, show how this flawed understanding of science makes it possible for a few scientists to doubt the general scientific consensus on, for example, human-caused climate change or tobacco. What they show is that if scientists are convinced that they are merely producing and communicating scientific truth, seeing themselves as a sort of subject that apart from the communicating this scientific truth has no role in, let's say, has no political, moral and ethical considerations when communication of science is done, that this makes scientific knowledge or facts mere tropes that can be used by anyone. After all, how can one realize, as they write, what real science is, and how can we separate from garbage science if we believe that all scientific facts are equal? When one thinks of what there is to be learned from history, including the history of science, it's still too often taught to provide direct lessons. In the COVID-19 crisis, for example, Dutch historians argued that they should be involved in consulting the policymakers about effective measures. Their argument was that it was them, after all, as experts of the past, who can tell what works and didn't work. And as example, they gave how the city of Milan in the 14th century combated the pest so successfully. Indeed, to some historians, the 2500 years old motto of Thucydides, the first so-called historian, this motto being that history is philosophy teaching by examples, is indeed still the main argument of what historians can contribute to public debates. The idea that history can teach direct lessons is for rather obvious reasons not very successful. First of all, historians themselves have showed that the past is fundamentally different as today. When historians cannot offer direct lessons from the past, then what is exactly what history can offer, or what historians of science can offer? I think there is a lot of answers being given to this, with the primary one being that history can offer a perspectival understanding of processes of the past, but also of the present and thereby the future. That is to say that historians can show how things in the past were similar, but also different at the same time, and how processes are not linear, but full of discontinuities, of moments where change seems to happen, but didn't happen, or where moments where change didn't seem to be likely, but in fact still did happen. Moreover, I think it can show that things we consider certain today, for example, certain scientific methods or facts, weren't considered certain or even the best method in the moment they were introduced. I think the history of science is a very good example of history offering such a perspectival understanding of change over time, as science and scientific facts, as well as scientific knowledge production, by so many in the public debate is seen as being unchanging, undoubtable, or at least how it should be, according to them, and as its or basis of how we see and understand the world. There are, of course, various approaches to the history and philosophy of science, but I think most of them can be categorized into two approaches or two perspectives, I would say. On the one hand, there is the so-called internalist perspective, and on the other hand, as it probably suggests, there's the externalist approach. Of course, with any distinction, you can say that it doesn't really exist, that they are two sides of the same coin, or rather that they are so different that they can't be considered two sides of the same coin. As the name suggests, externalist perspective cover a wide range of approaches that focus on how external factors influence scientific practice. That means scientific debate, scientific knowledge production, scientific concepts, how, for example, metaphors are used by scientists in everyday practice. The internalist perspective, as the name also shows, focus on the internal workings of science. Internalist perspectives of science, at least in the classical sense of the word, often focus on chronologically highlighting internal developments in science. This means from innovations to new scientific ideas, to methodologies, to debates, to scientists doing actually practice or experiments. And it often focuses on reconstructing the reasoning process that led to the acceptance of new scientific ideas. Before, and this is why I'm talking about the classical sense, this type was mostly done by retired scientists and mostly done of their own scientific field. Moreover, this internalist perspective is also what most science channels on YouTube usually cover. For example, they highlight how different scientific positions or ideas changed over time after new evidence became available. This is often done in the introduction of such videos. In these video narratives, more so, there might be a sort of externalist perspective coming up in the background, but this is never really the focus point or really considered a factor in scientific development. For example, one of my favorite YouTube science channels, PBS Aeon, on the history of biology and so, highlights how dinosaurs changed over time, and they imply or sort of suggest that these changes do not necessarily come from new evidence alone, but also from societal processes, but this is never really made clear in the argument. A better example is how the channel Veritasium, if I pronounce it correctly, goes into real depth by highlighting how these external factors, for example, in how they set research agendas, influence internal practices. This is actually very similarly to how self-proclaimed internalist professor of history of science at Cambridge, Hasok Chang, sees the uses of an internalist perspective of science. He, how could it also be otherwise, presents a more schematic view of internalist histories of science and shows that, or at least argues, that the history of science can contribute to scientific knowledge production in the present. Now let's look at how historians of science, coming from both the internalist and externalist approach, have tried to understand Einstein's revolution of physics. As I've said before, I think that Einstein's revolution of physics is a very good case study, for it shows how the history of science can help us better understand science today. This has several reasons. On the one hand, Einstein personally symbolizes for many people what a scientist is. And on the other hand, physics represents to many the most real, hardest, and most objective scientific field, most disconnected from external influences or politics. Moreover, since Einstein's introduction of quantum mechanics and theories of general relativity, various scientific fields have asked how exactly the revolutionary nature of these theories can be understood. This ranges from early brain scientists in the 1950s analyzing his brain, looking to discover what made him exactly a genius, to psychologists, educational experts, and also historians of science. There are a lot of better videos on YouTube that explain how exactly Einstein revolutionized physics and what it exactly means that he revolutionized physics, so I won't go into detail and assume a level of basic knowledge. Einstein's introduction of the general theory of relativity. Shortly after presenting his general theory of relativity in 1919, Albert Einstein became a media star of Weimar Germany. This actually happened relatively quickly, seeing how his new theory was directly understood to be a complete paradigm switch in physics. But at the same time, the story doesn't and shouldn't end here. What is often forgotten in this positivist narrative that is told in classrooms from primary schools to undergraduate classes in university is that his theories initially also created a widespread negative response, that various people in society, including renowned scientists and even Nobel Prize winners, reacted it. More so, that the revolutionary nature of Einstein's theories wasn't just in the internal theory or scientific findings, but rather also in the way he presented them. Indeed, it remains remarkable how theoretical many of Einstein's contributions were, often only empirically observed by scientists years or even decades later. This makes the question why his theories were relatively quickly accepted even more interesting, as science at the time, but even more so today arguably, is thought to be empirical first. Regardless of how historians of science define the concept of truth, a central understanding that internalist and externalist perspective often share is the idea that truth has no causal force drawn scientific beliefs towards it. This means that something we now consider scientifically proven or even empirically observably true is often not directly considered true at the moment of introduction or even observation. It is only after a long process of months or even years that it becomes accepted. And this process is not purely scientific. That means it isn't just involving experimentation, testing, theory building, but also social, cultural, and political processes. Like any historical process, the acceptance of scientific theories can only be understood retrospectively. A good example is the development of the compass, where between its discovery in China in the 4th century, it took hundreds of years for people to accept that it was better as navigating by the stars or by landmarks, and it only became more widely used in the 11th century. Other examples are the germ theory of disease in the 18th century and the theory of evolution by natural selection, that also took several decades to become more widely accepted. In the case of Einstein, historians taking an externalist perspective, for example, have highlighted that much of the critiques or attempts to reject Einstein's theories weren't in many cases directly related to the internal content of his theories. Indeed, their acceptance, as the argument goes, also wasn't solely due to pure scientific debate and validation. For example, some German conservatives labeled Einstein's theories as Jewish science, and they reacted them on this basis, while others, as communists for example in the Soviet Union, reacted them because they called it bourgeoisie science. A lot of the times it was actually a mixture of practical concerns and ideological motivated arguments that contributed to the reaction of Einstein's theories. For example, some prominent physicists such as 1919 Nobel laureate Johannes Stark reacted Einstein's theories not just because they lacked empirical evidence according to him, but also because they ran counter to the work that he had spent doing most of his career. In fact, Stark was one of the physicists who allied himself with the Nazis in an attempt to prevent acceptance of Einstein's ideas. On the other hand, in the Soviet Union in the 1930s, the work of Albert Einstein was attacked by communist philosophers and especially scientists who saw it as an example of irrelevant bourgeoisie science. This term, which was not widely used in the Soviet Union, stands for sciences that were considered unacceptable from an ideological point of view, at that time Marxist theory. Besides Einstein's theories, another example is how genetics was unacceptable in the Soviet Union in the 40s and 50s because of its role of chance, which was seen as incompatible with the universal laws of history. These debates about the work of Einstein actually led to the famous example of communist historian and philosopher of science Boris Hessen, who supported Einstein's theories and for this reason made a case study of Newton's science. In this book, Hessen argued that Newton's science also came from his social economic position. Hereby he intended to argue that when Soviet criticizers of Einstein accepted Newton's scientific ideas regardless of their supposedly bourgeoisie background, they should also do so with Einstein's ideas. Boris Hessen is actually considered as one of the first historians and philosophers of science, for he showed how Newton's theories were influenced by his social and economic position. For example, Newton's theory of gravity was impacted by the ballistics calculations of cannons at the time. Since then, many historians of science have still focused on how Einstein's work and theories are actually influenced by social, cultural, and political factors at the time. For example, in the 1970s, the US historian Paul Forman came up with what is now known as the Forman thesis. The idea that Einstein's theories were so rapidly accepted as true in Weimar Germany, not just because of the internal contents of the theory, but rather, in the years following Germany's defeat in the First World War, there was a widespread sense of crisis that led physicists to ardently hope for and actively search for, and also willingly to embrace, new theories of quantum. Although the Forman thesis has been criticized by historians and philosophers of science because it's argued for a strong causality between cultural factors and scientific practice, I still think it is interesting how he analyzed how important scientific concepts changed over time, as well as how this impacted the formation of the theory of relativity by Einstein. Forman analyzed, for example, how the concept of theory had changed in the late 19th and early 20th century prior to Einstein's work. Indeed, where a theory before was typically seen as a sort of provisional explanation for a set of phenomena that was subject to modification or reaction based on new evidence, Einstein's theory, at least initially, lacked direct empirical observational evidence. Hence, after his theories became more widely accepted, the concept of what a theory meant also came to be seen as more abstract and mathematical, a construct that could be primarily judged on its internal consistency and mathematical value rather than its ability to directly explain observations. With an important side note being that actually before Einstein's theory, there were also a lot of empirical observations that could no longer be explained by the old Newtonian paradigm, and there were also a lot of debates about this that influenced Einstein actually. Another interesting case that internalist historians of science have examined is the acceptance of Einstein's theory in Great Britain, where initially a lot of British scientists were skeptical of the theory, something that some external historians actually have linked to Einstein being a German scientist and the German scientific community being cut off from other countries, including Britain, and excluded from international scientific society since the start of the war. Internalist accounts show that how British scientists, as for example Arthur Eddington, a prominent astronomer, initially expressed doubt about Einstein's theory, arguing that it was incompatible with Newtonian mechanics. However, in 1919, Eddington led an expedition to test Einstein's theory during a total solar eclipse, and the results of this expedition provided a strong empirical support for the theory of Einstein. Another interesting example of how historians of science have tried to understand the introduction of Einstein's theories is how they looked at the changing concepts of causation and simultaneity. Prior to the development of Einstein's theory of relativity, simultaneity was generally seen as an objective and absolute concept, meaning that two events were either simultaneous or not simultaneous, regardless of their reference frame in which they were observed. Einstein's theory of relativity changed this idea by arguing that simultaneity was actually relative, meaning that it depended on the observer's reference frame. This reconceptualization of relativity of simultaneity had a significant implication for the concept of causation, as it suggested that the cause of an event might occur after the effect in one reference frame, but before the effect in another reference frame. Again, historians of science have argued that these reconceptualizations were also strongly dependent or impacted by changes in society at large. I think this is best expressed by historian of science Jürgen Renn and professor of theoretical physics at the Humboldt University of Jerusalem, Hanoch Gutfreud, in their introduction of Einstein's autobiography. As they show, his scientific breakthroughs are intimately connected with his epistemological reflections on fundamental concepts such as space, time, and causality. And this in turn, as they argue, but Einstein himself as well wrote, comes from his position in that moment in time and his reflection on history, including the history of physics and science itself. There are of course plenty of other articles that show how external events shape science, as for example this article on how Einstein's theory was saved by the outbreak of the First World War. At the same time, these kind of interpretations still present the external and science as being separate spheres that interfere but are not permanently intertwined. Before I give 5 reasons why I think external factors should be taken into account when understanding science, I want to highlight that at the time, this actually was also a question posed by important scientists, including Einstein and Schrödinger themselves, as these quotes show. What does the history of science tell us about science today? 5 perspectives from the case of Einstein and the limits of these. First perspective. Einstein's political views, cultural background, and historical time period may have influenced his work as a scientist, but they were not the sole cause, nor a prerequisite of his scientific achievements. That is to say, it can be true that science is based on a careful observation and analysis of empirical evidence, but at the same time it can be true that it's also a human enterprise that is subject to the biases and influences of the scientist who produces it, as well as the institutions where science is produced. Hence, the often heard argument today that scientific knowledge should be objective and free from human influence is actually a myth and can lead to a misunderstanding of the ways that science is produced, accepted, and also how it is influenced by social and cultural factors that are part of the scientist. Perspective 2. Science is a historical practice, meaning that it's constantly evolving, coming from something and with the aim towards something. That means that the value of scientific ideas, discoveries, and inventions change over time, both depending on social needs, cultural factors, and values. From the conception of scientific research ideas and societal needs, or the cultural imagination shaping the young or old scientist in particular ways, to how gender, social relations, education, tradition, and institutions funding certain scientific endeavors or methods and others not, science indeed intertwines with politics and society. But this also means it can't be the sole factor of explanation of scientific knowledge. Science and scientific knowledge in that case should be understood in what Germans call the Jetztzeit, or present moment in time. This doesn't mean absolute relativism in saying that science is always judged and valued by its time, after its conception. I don't believe that something being time dependent makes it also not able to be valued or disvalued on today's ethic norms. Historians don't need to be ethics relativists even when noting that ethics change over time. Perspective 3. Innovation and science. Scientific concepts change. This means that this change could be understood as part of the external and internal processes of science, the debates, how scientific theories become rejected, accepted, what are considered methods that lead to scientific facts, how does this method relate to the theory, and how does theory relate to the method. Scientific practices change. How does the relation between the methods change, and what does this say about science today? Perspective 4. Identifying external factors that shape scientific practices. Appreciation and acceptance of scientific theories is partly politically motivated. Scientific debates can be politically motivated, funding is politically motivated, and hence internal aspects aren't the only things that count. Indeed, as in all sciences, causation in history is a very hard concept, and it's not a statistical method, at least not yet. I'm sorry, Humboldt. Perspective 5. Analyzing science. From generalization to localization versus the global, indeed, making historical arguments about science is difficult, and it's dependent on the time, the viewpoint, the selection of sources, and the argument. What does one element say over the whole cause? Or what does one cause say over the whole global scientific process? And vice versa. Yes, the historian of science is also politically motivated, but in the end, showing that the scientist or an historian is coming from a certain background and is working from a certain position that influences his or her ideas, theories, and sources selection isn't discrediting or reducing the value of the scientific theory itself. Final perspective. How the history of science can provide a perspective on how scientific knowledge functions today. The controversy surrounding Einstein's theory of relativity and acceptance of scientific theories, including his, despite this controversy, can help us better understand both the nature of science and the way that scientific ideas are evaluated, accepted in society and in both scientific communities. One understanding is that scientific theories are often met with resistance and skepticism, and that it is fueled by external factors, especially when they challenge existing established ideas or worldviews or threaten to disrupt existing power dynamics. Today that is definitely the case with climate change. For example, many conservative thinkers and groups have attacked the scientific consensus on climate change as being based on theories lacking empirical basis, despite the overwhelming evidence in support of the theory. This criticism has often been fueled by the fossil fuel industry, which has a financial interest in denying the existence of climate change and has been shown to fund efforts to create doubt about the science behind climate change. Hence, when Elon Musk says that it's just about continuing testing, not believing the theory because it's leftist science, this is in fact the same as others, 100 years ago, argued about Einstein's theory. What the history of science therefore can offer is a non-linear conception of history, of science, and of scientific knowledge. When what we remember of the past is only there because of the present, which looks inevitable and unchanging, the idea of the future, although we might expect it to be new, is in fact hollow and bleak. The history of science can therefore offer us a perspective to understand the complex interplay of internal and external factors that shape scientific knowledge, that recognize the ways in which our understanding of current-day science is shaped by the present. That is to say, the ultimate usefulness of the perspective that the history of science offers is a processual understanding. The last example of this is therefore a personal one. In the initial days after the first COVID-19 lockdown in 2019, various historians in the media wanted to remind us of the life of the scientist and mathematician Isaac Newton. They wanted to show us how we could spend that period of the quarantine more useful. Indeed, Newton, as a 23-year-old student, they reminded us, came out of the year of quarantine as the discoverer of the law of gravity and professor. This kind of monumental historical narratives, as Nietzsche so rightly noted, deprives us of the hope to ever emulate greatness. And besides, it's also simply false. It suggests that time is continuous, and that what is useful now is also useful tomorrow, the next year, or over 200 years. It is crucial to understand that Newton was obsessed and probably spent more time with practicing scientific practices that today are regarded as pseudoscience, alchemy, the discovery of gold, and theology, and that he, nor people at his time, could have known that in the process of history, these in 200 years would be regarded as less valuable than the other. What the history of science therefore offers is a perspective of non-linearity. Going back to Newton, the perspective that the history of science offers is not what he did in his year of wonders and feel guilty about or own useless activities, but rather focus on how and why he did come up with his laws of gravity in this year. His year of quarantine did not become his year of wonders because he planned it to be. Rather, his discovery came to be through an interplay of external and internal factors, shaping his interest, his education, his curiosity, factors that instead of him spending days inside classrooms in Cambridge, improving his human capital, working on his theory building, in fact allowed him to sit outside of his parental house in the garden and, well, as the story goes at least, watching the apple tree wave in the wind until ultimately one apple fell.